Hi everyone, my name is Jianbo Jiao. I'm glad to be here to present our work Self-Supervised Contrastive Video-Speech Representation Learning for Ultrasound. This work mainly focuses on self-supervised learning and targets video and speech audio multimodal data. We also incorporate contrastive learning to further regularize the learning process. Self-supervised representation learning is also termed as unsupervised learning in some work, indicating that no external supervision signal is required during the learning process. It aims to extract knowledge and representations from the data itself, and the supervision also comes from the unlabeled data. This is like our humans that learn just from observation. Self-supervised learning is quite useful for the current data-driven era where human annotation is expensive to acquire, especially for scenarios like medical imaging. The basic pipeline for self-supervised representation learning is like this. First, a deep model is trained on a large-scale unlabeled dataset with the objective of some pretext task. After that, some downstream tasks with a small number of labeled data is used to evaluate the quality of the learned representation. Here, the representation is transferred to the model of the downstream task. Another technique we leveraged in this work is contrastive learning. Here is an example. 3 inputs of an anchor, a positive sample, and a negative sample are encoded by deep neural networks to feature vectors, and then further mapped to a feature space as shown on the right. The anchor and positive sample are encouraged to be closer to each other, while the negative sample and the anchor are repelled. This is the basic idea of contrastive learning. This work is mainly based on a large-scale clinical ultrasound dataset, in which both the scanned ultrasound video and the corresponding speech audio from the sonographer are available and aligned. In this work, we focus on self-supervised representation learning by modeling the correlation between these two data modalities. Now I'll describe the proposed approach. Our assumption is that these two modalities of ultrasound video and speech audio have correlations in a projected embedding space. For example, here is a short ultrasound video and the corresponding audio signal. For the video and audio describing the same content, they should have high correlations, and when projected into the embedding space, they should live close, as highlighted in green. On the other hand, if the video and audio clips describe different content, they should live with a large distance in the embedding space, as highlighted in red. Based on this assumption, we first propose a baseline method to model this correlation. The ultrasound video is fed into a video network GV, and the audio data is fed into a speech network GS. Following that is a fusion operation to combine the feature vectors from these two modalities. The objective is to predict if the input samples are correlated or not. So it's a binary classification problem. To train this model, we need to define the positive sample pair and negative pair. Here, the positive pair is considered as the video and audio data that are well aligned at the same location, and the negative pair is the video and audio data at different locations. In order to encourage the model to learn stronger representations, we further define hard positive and hard negative pairs, in which the hard positive means the video and audio samples are within a similar anatomy, but not at the exactly same position. The hard negative pair indicates that the video and audio samples are with a distance, but not that far away as in the easy negative pair. Due to the nature of speech audio, the content is not always correlated with the corresponding video, even though they are aligned to the same time step. As a result, in addition to the correlation modeling, we introduce cross-modal contrastive learning. Specifically, the features from the video and speech networks are further projected to a new feature space by a nonlinear mapping function H. Then these new features, along with the features from other clips in the training batch, are leveraged to optimize the contrastive objective, where the positive samples are encouraged to be similar and negative samples forced to be away from each other. Here is an example of the case where the speech audio is not correlated with the video data. There is also lots of background noise. For example, we can hear that there is noise from the air conditioner and the button clicking.
That's normal. There's the cerebellum here that I mentioned on the last one. It's quite easy to get a falsely elevated buccal fold measurement, which is why I've repeated it, but that's fine. Hello. Have you got my clipboard?
Now there comes a non-narrative random talk between doctors.
Got one, did you have two? The other one, I think, something French. Did they know that? As in, I didn't bring it in here, it's, I think, how much reception. Yeah. Let's make sure this blood is
Again, another kind of noise from the ambulance. As a result, we further propose an affinity-aware self-paced learning scheme to address these problems. The affinity is defined as the relevance between video and audio. Then, based on different affinity, different learning curriculums are applied. For simplicity in this work, we only consider low affinity and high affinity. For example, in this part where the audio is not relevant to the video, it is not included in the learning process mentioned above. Instead, only the remaining relevant video-audio data is fed into the model. Although this part is irrelevant, we assume that there is still representations can be learned from the video itself. So instead of totally abandoning all this data, we further apply a video-based representation learning approach to the video data alone. Here we let the network to predict the correct order of a reshuffled video. Next, I'll show the experimental evaluations. First is the setting. We use ResNext 50 as our backbone networks with the squeeze and excitation module and dilated convolutions. In each video clip, we randomly sample two groups to represent this clip, although more groups are encouraged if the memory is sufficient. For the sampling of hard positive, the skip interval is set to 5. We use a large-scale ultrasound dataset pulse and 81 scans with speech audio with about 73,000 clips in total. Each sample pair or group consists of one video frame and audio signal of 0.6 seconds. The audio data is converted to a 2D log spectrogram using a short-term Fourier transform before fed into the network. In order to evaluate the quality of the learned representations, we follow the pipeline of representation learning in natural images by transferring the learned representations to downstream tasks and evaluate the performance accordingly. The first downstream task we use here is a standard plane detection, which is a 14-category classification problem. From the result, we can see that our method, the blue bar, improves the random initialization significantly and performs better than the video-only solution and the model initialized from ImageNet weights. SonoNet is a fully supervised method with expert annotations and is taken as the upper bound. We also present the confusion matrix for better understanding of each category. We can see that those cardiac-related categories are with relatively worse performance. These categories are even difficult for human experts. When using our self-supervised cross-modal representation learning approach, we can see that compared to the random initialization shown on the left, each category is improved a lot, especially for those difficult cardiac-related ones. This validates the effectiveness of the proposed method. In addition to the classification-based downstream task, we further include another regression-based task to validate our method. Here we use the task of eye gaze silency prediction, which aims to predict the eye gaze region of the sonographer when scanning the ultrasound. We can see that our method again performs much better than other solutions. Note that it even performs better than the SonoNet, which is a fully supervised method as mentioned above. On the right shows some qualitative results, which also validate the effectiveness of the proposed method. Finally, we did an ablation study to investigate the contribution of each component. The left shows performance for the standard plane detection, while the right side shows the task of eye gaze silency prediction. Starting from the baseline where only audio-video correlation is considered, when adding the cross-modal contrastive learning, we can see that the performance improves significantly. By including the affinity-aware self-paced learning scheme, the performance is further improved. To conclude, in this work, we present the first cross-modal self-supervised representation learning approach for ultrasound. Two modalities of video and narrative speech audio are considered. To address the unrelated issue, we propose cross-modal contrastive learning with an affinity-aware self-paced learning approach. In the experiment, we demonstrated comparable and even better performance than fully supervised solutions. Although in this paper only showcase ultrasound data, the proposed approach is readily applicable to other domains. That's all. Thank you for your attention. More details, please refer to the paper.